Okay, good morning. So welcome to the second video lecture. So in the last class, we have seen the definition for static characteristics as well as dynamic characteristics, and we have seen the different, we have listed the different static characteristics. Then we started with the static error, and yesterday we defined what is the true value and what is the measured or the actual value, and then we have computed the static error. And while taking one example, that is, if you are making 1,000 amps uh, ampere reading, then a static error of plus or minus 2 amps is negligibly small. But the same error plus or minus 2 amps, if you make while you make a measurement of 10 amps, is considerably large error. So simply specifying the static error doesn't make any sense. Okay, so there is another way, that is always error is actually specified in terms of percentage. How much percentage of true value is the error? That is the way we have to go. So that is where we have the relative static error important. So that is nothing but the epsilon r, and as I define, this is the value eta r, or epsilon r is nothing but epsilon naught by 80. So how do you express in percentage? Simply multiply by 100, you get in percentage. Okay, now from this equation 2.1, so from equation 2.1, that is delta A is equal to measured value minus, so this is the static error, measured value minus true value. So instead of from here we can get true value is equal to am minus delta A. So this delta A is nothing but epsilon naught. Then epsilon, that is equal to epsilon naught, you can write it as, what is it, epsilon naught, that is this much epsilon naught is equal to ER 80. That is what you can write. That is epsilon naught by 80 is equal to ER. From here, eta r multiplied by 80 is nothing but epsilon naught. You can substitute that. From that, you group the terms of AM 80, and 80 is nothing but AM by 1 plus epsilon r. So this is the relation between 80 and AM, that is the true value and the measured value in terms of relative error. So if you know the relative error, you can get the value for true value. So 80 is nothing but AM multiplied by 1 minus epsilon r. Okay, now so this is the relation between relation between 80 and AM in connection with epsilon r. And then another, if we have an error, simply seeing an error doesn't make any sense. You have to make corrections. So how do you make that correction? So correction obviously is the opposite of the static error. That is, if error is positive, then the correction will be negative. Likewise, if error is negative, correction will be positive. So we know that the static error is AM minus 80. So of course the correction will be 80 minus AM. Or we can write that is correction is nothing but negative of delta A. So here are a few examples. You can just go through that. I'll just take a typical example. A thermometer reads 95.45 degrees Celsius, and the static correction given in the temperature correction curve is minus 0.08 degrees Celsius. Determine the true value of the temperature. So we know that true value is nothing but this, that is AM minus delta A. Minus delta A is nothing but plus delta C. So we have this one here. So plus delta C is nothing but minus 0.0. Correction is minus 0.0. You just simply put that value here. That is the 80 is 95.37 degrees Celsius. So this is how you apply things in a practical situation. Okay. Now, so that is all about static error and relative error. Then this curve is very important. You have to plot such a curve in many of the experiments in measurements lab. This curve is called error calibration curve, or simply calibration curve. Calibration I already explained in a preliminary way. That is, you have something in your hand, you have some device, some measuring apparatus in your hand. It can be ammeter, voltmeter, it can be resistance, or ohm meter, anything. So that indicating meter is compared with a standard, with a working standard. Okay, so while you compare, you actually end up in finding so many relative errors or static error. Usually that is specified as relative error. So that error, really percentage error specified against the measured value or the true value, will give the calibration curve. How much error we have while I measured this much, while I measured this value, what was the error? While the measurement was this measured value was this quantity, how much percentage error was here? So you can see that while the measured value was somewhere around here, you have the error, a positive error, maybe a 0.5 percentage error. Then while it was around 20, the measured value, the error, the percentage error was around 0.35 percentage. And you can see that at 90, at the value of 90, the measured quantity was 90, the error is maximum, that is around 1.25 percentage. So you can see that you can get an idea of idea of how error varies. Error is not a constant. So while we make different readings, percentage error also varies. So such a curve will give an idea how much error is induced in the measured value. So this is very important. Calibration curve helps in making corrections. Okay, so that is very important. Then scale range and scale span is also very simple to understand, because while you make while we take an instrument, obviously it has a minimum value and maximum value. That is, suppose if an ammeter has a range from 0 to 100, then of course the minimum value of amps is 0 and the maximum amps that can be read through that ammeter is 100 amps. Beyond that, that's not possible. So the span is nothing but the maximum value minus the minimum value. That is, if you take a 0 to 100 amps ammeter, the span will be 100 minus 0, that is 100 amps. Or if it is suppose if you take a thermometer, if the minimum scale is 200 degrees Celsius and the maximum value is 500, then the span is 500 minus 200, that is 300 degree Celsius. Okay. Now another thing is, that is another static characteristic is called the drift. What is drift? That is the movement of, you have some measuring quantity. You want to measure some quantity, but there is some drift, initial drift. Okay, that can be of varying reasons. Okay, that is that some value is automatically being added every time when you make a measurement. Some value, that value can be constant value, or that can be some linearly increasing value. Okay, so that value is constantly being unknowingly being added to the measured quantity. You are taking out the reading and you believe that the readings you have taken are true, but that is not the case. Unknowingly, without your knowledge, some value is being added. It can be constant value or it can be a linearly varying value with respect to reading. So such a value which is being added throughout the reading is called drift. So we have to avoid that drift, because such a offset is being crept in the readings, so that should be avoided. So I made a statement that sometimes the value can be constant. So that is the first case. That is, there are three types of drift. The first one we'll see, that is called zero drift. That is, your pointer, before you make any reading or before you apply something to a measuring instrument, then before that you have to ensure that the pointer coincides exactly on the pointer lies on the zero value. Otherwise, what happens? The zero error will be coming inside. So sometimes the pointer will be below the zero pointer, or above the zero pointer. Okay, so it can be dealt in two ways. Many of the times the meter will have a button, a knob over the meter, where you can adjust the pointer using a screwdriver. Okay, so that can be done. Otherwise, if that is not there, if you are aware of that such a drift, if you are aware that the pointer is shifted above the 0 point or below the 0 point, if you are aware of that value, then you simply make the readings and then make corrections. If it is a positive value of drift, then the correction should be negative, and if the 0 pointer is below the 0 point, then you can make some positive corrections. That can also be done. So zero drift is that it can be easily shown from the graph. That is, see, actually this should be in this way. That is, this is the nominal characteristics. That is, the zero should be exactly at this point, but you can see that when the quantity under measurement is 0, the reading of the meter is somewhere here. That is, this much is the zero drift. The output initially have a value. So the characteristics Ideally, this should be in this way, but the characteristics also shift by this much, the zero drift. Another drift is called span drift. I'll show the graph. Span drift is that is this should be the characteristics, linear characteristics. So with respect to the variation of input, output also varies linearly. But you can see that there is a linear variation of values from this value to this value. That is, when the input varies linearly, input varies, the output also varies, or the output also varies, but the drift also varies linearly. That is, the drift increases as the readings increases. As the input increases, the readings also, the drift also increases. The drift also linearly increases. You can see that the shift here, only this much shift is there. Here this much shift is there. So here the quantity increases, the drift also increases. Here the quantity increases, again the drift increases. And at this point, the measured quantity is maximum, the drift also is maximum. So the drift also increases linearly. Another thing is that, so that is the combination of the zero drift and span drift. That is, so both zero drift is there. This is zero drift, and also the span drift is also there. The span also, the difference also is increasing linearly. So this combination is also possible. Now, this is actually the drift. This is another undesirable quantity. And next is the reproducibility. This is another characteristic that we have to learn. That is reproducibility. Reproducibility means that is a closeness with a given input, which may be measured over and over again. That is the closeness. You make so many readings. How much close is such readings? I yesterday pointed out one thing, that is, if you make 7 readings, out of 7, 5 will be very close. You can take it as a cluster, or you can see that there is an agreement between these values. So you can take that five readings, and you are discarding the 2 readings because it is not at all consistent with the rest of the 5. That may be due to some random error or some other reasons, which is totally out of control of the instrument or of the operating personnel. So reproducibility is the closeness of the measurement. That is, when we take the readings over and over again. That is, this is the ideal true value, but the measured quantity is in and around this true value, true value. Or you can establish a tolerance band, so that if the readings culminate within that tolerance band, then you can tell that the reproducibility of the measuring instrument is good. Or if the measurement, if the quantity and if the readings are very vague and very outside that tolerance band, and somewhere, and this time it is here, another time it is somewhere else, then you cannot tell that the measuring device is a good reproducibility device. So reproducibility or repeatability is an important characteristic, which is a necessary, a very desirable characteristic that a measuring device that should have the closeness to the given true value. So it should be in and around a band, a tolerance band. Then another thing is that accuracy. So accuracy and precision is another thing. So there are 3 types of accuracy. One is the point accuracy. So what is point accuracy? So on a scale you have so many points. At this point, this is the accuracy. So that is called point accuracy. Maybe an ammeter may be defined. It's having a scale from 0 to 10 amps. There is a point called 5 amps point. At that 5 amps point, this is accuracy. So the accuracy is only defined for that 5 amps point. We don't know what is the accuracy at 4 amps. We don't know the accuracy at 6 amps. So the accuracy is defined only at that 5 amps. Such an accuracy definition is called the point accuracy. That does not give any idea about the accuracy at some other point. Okay, so that is one way of indicating point accuracy that is rarely used. Another one is accuracy specified as percentage of scale. That is, we have a thermometer from 0 to 500 degrees Celsius, and if it is specified in terms of scale range as a percentage, that is, 500 may be expressed as plus or minus 0.5% of scale range. That is, accuracy specified as plus or minus 5% of the scale. This I'll take in the next class. So next class we'll complete the static characteristics. Till then, goodbye.